All right, welcome. In this video, I'm going to be doing some double integrals that require a Jacobian change of variables. I'm going to be working through multivariable calculus homework 3.8. So let's just get to it. Here we've got a double integral that we are integrating over a kind of a diamond region, which is just kind of the perfect situation to use a Jacobian change of variables. Because, computing the Jacobian itself won't be that difficult, and, it'll be pretty straightforward. So I'm over here and I'm seeing, pardon me. Okay, I'm seeing these two sides are parallel, and when you have a parallelogram, it pretty much always works the same. This is, I'm going to write down an equation for these lines. This is y equals x minus 1, and this is y equals x plus 1. Okay? I'm going to say that this is x minus y equals negative 1, and x minus y equals positive 1. Okay? Then I'm going to go over here, and I'm going to say that this line right here is y equals 1 minus x, which I could work around to say x plus y equals 1. And then over here, this is x plus y equals negative 1, or y equals negative 1 minus x. And I could add x to both sides and say x plus y equal negative 1. Okay? So I'm going to let u equal x minus y. And I'm going to let v equal x plus y. Okay. And in order to actually, compute my Jacobian, I need to get x and y in terms of u and v, if possible. If it's not possible, we've got a couple of examples later on in this problem set, and I'll show you what to do when that happens. Okay. I'm going to start by kind of solving for x and y by solving the system. I'm going to start by adding these two equations together. Okay? And I'll get 2x equals u plus v, meaning x is half of u plus v. Okay? And then I'll subtract the equations from each other. I think I'll do red minus blue, and I'll have v minus u is equal to 2y, so that 1y is half of v minus u. Right, v minus u, y minus negative y. Yeah, okay, feel good about it. I think this is different from how I worked it the previous time I worked this problem, but it'll be all right. Okay, now we're going to find the actual Jacobian, the determinant of the Jacobian matrix. Okay, so I'm going to say determinant of J is equal to the determinant of, all right, it's xu, xv, yu, and yv, right? So I'll just kind of take these one at a time. The derivative of x with respect to u is going to be 1/2. Oh, whoops. The derivative of x with respect to v is also going to be 1/2. The derivative of y with respect to u will be negative 1/2. And the derivative of y with respect to v will be, hold on, what am I thinking? That's a positive half. I don't know why I was tripping on that. Okay. Either way, I take that determinant. I'm going to multiply 1/2 by 1/2 there. And then I'm going to subtract 1/2 times negative 1/2. So that's 1/4 minus negative 1/4. And that's equal to 1/2. Okay. Okay, now we're going to compute convert our integral into u's and v's. Okay, so 4x squared plus 4y squared. Maybe I'll call that 4 times x squared plus y squared. Oh, yeah, and I remember I've done this before. I'm going to actually do that right now. I'm going to do x squared and y squared. X squared is going to be 1/4 of u plus v squared. Well, that's going to be u squared plus 2 times u times v plus v squared. And y squared is going to equal 1/4 of, okay, that'll be v squared minus 2 times v plus u squared. Okay, so just put those together. Then, if I'm going to put x squared plus y squared, that will be equal to 1/4 of 2u squared plus 2v squared. Okay, and 4 times x squared plus y squared would just be equal to 1 of those 2u squareds plus 2v squareds. As a result, my integral is going to become, I'm going to need quite a bit more space. Just move that up here. My integral is going to become a double integral. I'll worry about the u and v bounds later, of 2u squared plus 2v squared multiplied by the determinant of j, which is a half. So I've just got u squared plus v squared. Okay, and so, you see that it doesn't matter which one I start with. Maybe I'll do v first. V is x plus y, and that's running from -1 to 1. And du, okay, u is running also from -1 to 1. So, okay, here we go. And we're going to, I might just zoom back in on this for a second and just actually perform the integration steps. Whoops. All right. So with respect to v, I'm going to have u squared v plus 1/3 v to the third as v runs from -1 up to 1. Okay, it's going to give me u squared plus 1/3 v to the third minus, when I plug in -1, I'll get negative u squared minus 1/3 v to, no, pardon me, v is 1. Yeah, so plus a third. U squared minus a third, because -1 to the third is -1/3. Okay, so what this is 2u squared plus 2 divided by 3. Okay, and we're going to integrate that from -1 to 1. 2u squared plus 2/3 du. And we can do this. We're going to say, all right. From -1 to 1, and that's going to be 2/3 plus 2/3 when I plug in 1, and then when I plug in -1, I'm going to get -2/3 minus 2/3. So in total, that's going to be 8 divided by 3. And maybe I'll zoom back out so you can see the whole thing. Number 2. Compute the integral of y times x minus y dA over this region R. Okay, so I'm going to let this be, this is like a y equals 0 and a y equals 3 line. So I'm going to let v equal y because, v comes after u. Y comes after x. It doesn't really matter. I should probably take this time to emphasize that your choice of u and v, it really doesn't matter. And even later choices you make may make your work look a little different, but it shouldn't impact the answer. Okay, this is going to be y equals x minus 4, I think. Yeah, and this is going to be y equals x. Okay, so kind of like I did last time, I'm going to call that x minus y equals 4 and x minus y equals 0. So if I let u equal x minus y and v equal y, then I'll be able to, I'll be able to do this pretty easily. So kind of the next thing I need to do is take these and get x and y in terms of v. Y equals v, we already know that, that's going to be pretty easy. X is going to equal u plus y, but we know y is v, so that'll be u plus v. Okay. And then I think I'm going to find my Jacobian, so the determinant of j is going to be equal to the determinant of xu, xv, yu, yv. Okay, xu is 1, xv is also 1, yu, I don't see any u's, so that's going to be 0, yv is going to be 1. Okay, that determinant is 1 times 1 minus 0 times 1, and that's going to be 1. Okay. So I don't really have to worry about an area scaling situation. And so I think now I'm pretty much just ready to convert this to a double integral over, UV space, where v, I can see here, is running from 0 up to 3. So maybe let's see. X minus y. Oh, that's u. And it does not matter, so I guess I'll just do 0, 3. Let's see, whoops. Maybe I'll do that on the outside. It doesn't matter. 0 to 3, u is x minus y, and that's going from 0 to 4. And then, okay, y, that's v. And x minus y, that's u. And then, okay, blue is u, so I need to do du. But it's times the absolute value of j, which is just going to be 1. So I might even put in there. Du and then dv. So the antiderivative here is 1/2 u squared multiplied by v as u runs from 0 up to 4. Okay, when u is equal to 4, I've got 8v. Minus when u is equal to 0, I have 0v. Okay, so it's going to be the integral from 0 to 3 of 8v dv. And that's going to be 4 times v squared as v runs from 0 up to 3. And that would be 4 times 9, which is 36. Here's an example of one that we're going to need to use, a little bit more trickery on. We're going to need to use kind of like the inverse of the Jacobian matrix, which we can use linear algebra techniques to find. Okay, it'll be all right. So what I'm going to do right now is I'm going to kind of work these equations around to get them a little bit more implicit. I might make this just slightly larger. And so I'm going to say, all right, y equals 1 over x and y equals 4 over x. That's x, y equals 4 and x, y equals 1. It seems like it's good to write these things more implicitly to get the u's and v's, is what it seems like to me. Now, y equals 2x and y equals x over 4, you might be looking at it like, what am I supposed to do here? I think what I'm going to do is I'm going to do x divided by y is going to be a constant. You can do y over x. This is what I was saying earlier. You can do these things and, make them make some choices along the way that may be different from the choices I'm making, but it shouldn't impact the value of your integral. So I'm going to say, all right, x divided by y equals 1/2. And I just like this because I was thinking about, as I move left to right, I feel like I should be getting, larger. And I think I'm going to let that be u. Okay, but you don't have to do that if you don't want. You can do y over x. I know some people in my class did y over x, and they got the exact same answer as me. So that must mean that you can do whatever you want. So x divided by y is equal to 4. Okay, that will just change your bounds of integration later on. Instead of going from 1/2 to 4, they'd be going from, I think, 1/4 to 2. But I can agree about that. X over y. Okay. I'm going to let u equal x over y. And I'm going to let v equal x times 1. Now, one thing that I showed y'all in class was that the inverse Jacobian matrix, I can get that by taking ux, uy, vx, and vy. Okay, and then I'll use a property of determinants to find the determinant of j. And I really like this. Okay, I verified that this is a legitimate thing to do, and this is much faster, especially because, I don't know, maybe you know how to solve this system for x and y in terms of u and v, but you don't need to. And this is much easier. I like this. Okay? So ux, the derivative of u with respect to x is going to be 1 over y. Okay, uy, the derivative of u with respect to y. Now, okay, if I've got x, y to the negative 1, I want to take the derivative with respect to y. I'm going to have negative x, y to the negative 2. But I might like to write it a little differently than that. I might call it negative x divided by y squared. And, right, so vx is going to be y. And vy will be x. Okay? Okay, so the determinant of j inverse is going to be, all right, I'm going to multiply 1 over y times x. And I'm going to subtract negative x y over y squared. Okay, but wait a second. Y over y squared is 1 over y. Negative, negative, and I can make that plus. That's going to be 2x divided by y. Now, I know that, whoops, ran off my shot. Yeah, that's better. I know that I'm eventually wanting to turn these into u's and this integral into u's and v's, and so it's going to be 2 times u. Okay? Um, okay, but I'm not looking for the determinant of J inverse. Okay, I'm looking for the determinant of J. Okay, and so we're going to use this fact from linear algebra that the determinant of the inverse matrix is equal to 1 over the determinant of the original matrix. Okay. Or I guess I could write it as the determinant of A is 1 over the determinant of A inverse is what I'm really going to be using, but we know that the inverse of the inverse is the original. So we're going to say that the determinant of J is equal to 1 divided by 2u. Okay? And this is going to be much nicer than whatever we would have done. Or maybe you did it. Maybe you solved the system for x and y in terms of u and v, and it wasn't. Let me know. But I've got my Jacobian determinant. I'm ready to move on. So I'm going to be double integrating e to the negative half of v multiplied by 1 over 2u. I'm going to factor out the half. Okay, and I think I'm going to do du and then dv. Okay. I did dv and then du, and I didn't like it as much. The students in my class suggested du and then dv, so we're going to do that one. Okay. U runs from a half up to 4, and v runs from 1 to 4. Yeah, because v is the xy. Yeah, I see it now. Okay, I'm definitely going to need more room, and maybe I'll just kind of focus on this integration now. And okay, I'm starting with the antiderivative with respect to u. And I'm really just going to work on a u level right now. This is giving me log of the absolute value of u as u runs from 0.5 up to 4. Okay, which is log of 4 minus log of 0.5. Okay, I know that really I've got an e to the negative half of v attached to all of this stuff, but that's going to have to stay inside the integral, and then I'm going to factor out log of 4 minus log of 0.5. That's just a constant, so I'm going to factor that out into the front of the integral. So I've got half of log of 4 minus the log of 0.5 times the integral from 1 to 4 of e to the negative 1/2 v dv. Okay, now when I anti-differentiate e to the negative half of v, I'm going to get e to the negative half of v. Probably be writing that a little more clearly, negative half of v, but I'm going to need to also divide by negative half to prepare for the chain rule. Okay, and so I'm still going to do that, but actually maybe I do this and I throw in the negative 2 later, or maybe I work kind of on that level. But anyway, I'm going to say v runs from 1 up to 4, which means that this is equal to negative 2 times e to the, okay, when v is 4, that's negative 2, minus e to the negative half of 1. Okay. So in total, I've got, okay, I'm going to combine that negative 2 with a half to make a negative 1. And all the rest of the numbers will stay the same. And, well, that was kind of a lot, but there it is. Okay, there it is in its totality. All right, number 4. Compute the double integral over region D. Whoops, I didn't even catch that. Let's see if I can just cover that up. Yeah. I don't know if it's going to go behind the white. I hope not. Integral over region D of y sine of xy dA. Okay. So I'm going to let these top and bottom lines be my v's, and this is y equals 1 and y equals 4. I'm going to let v equal y. Okay, that part will be easy. And this will be pretty similar to the one we just did, because it's y equals 1 over x and y equals 4 over x. So I'm going to let u equal xy. Okay, and this will be, xy equals 4, and this one would be xy equals 1. I think this is one that I did kind of do some work on, and I found that you can solve this one back for x and y pretty easily. I think I might just use that inverse determinant thing again. I really like that. I only recently discovered that was even an option, and I've been teaching this class for an embarrassingly long period of time to not know that, but I know it now, and I'm going to use it. So I'm going to say, all right, J inverse is the matrix ux, uy, vx, vy. Feeling like that's not the matrix I got earlier. Hold on. Yeah, that's the exact same matrix I got earlier, so I'm not remembering right. So I know that that means that the determinant of J inverse is equal to y times 1 minus x times 0, which is going to be y. That tells me that the determinant of regular J is going to be 1 over y. And now I think I've got all the pieces I need. I'm going to be double integrating y, which is v times the sine of u. Okay, and then the absolute value of j is going to be 1 over y, which is the same as 1 over v. I was like, wait a second, I thought I was out of the xy world. Yeah, I probably should say that's 1 over v, because v and y are the same. Okay. So I'm going to say divide times 1 over v. I'm going to do du and then dv, and we're going to be double integrating over, some d prime, like this, the rectangle whose image under the transform j is d. Okay. But what we can do is we can cancel off those v's, and we can say that this is sine u du dv. U is x times y running from 1 to 4. And v is y, which is also running from 1 to 4. Okay. So the antiderivative for sine u with respect to u is negative cosine of u. And we're going to let u run from 1 to 4. That's kind of unfortunate because it's like, well, all I can do is say it's negative cosine 4 minus negative cosine 1. Wait, cosine 4, negative cosine 4. Okay, I was like, I know that one of these has to be negative. I mean, it's negative cosine 1. And so I might call that cosine 1 minus cosine 4. But cosine 1 minus cosine 4, that's just a constant. That's probably not the... And then I'm just integrating 1 to 4 dv. We know that's going to be 4 minus 1, which is 3. So I get 3 times cosine 1 minus cosine 4. Whoops. Okay. And, well, that's how we did that one. All right, number 5. Double integral over region T of e to the xy dA, where T is bounded by xy equals 10 and xy equals 20. I'll show you that it looks like the red curves here are xy equals 10 and xy equals 20, just thinking about these points right here where x equals 2. Okay, I'm going to let v be that. Okay, so I'm going to have v equals, what is it, xy. And I'm going to have u equals x squared y. This one is one that I was able to solve for x and y in terms of u and v. I started by dividing the blue equation by the red equation, which is something you can do algebraically. And then I just kind of went from there. And I verified that it did work out the same as what I'm about to do, which I think is a little more straightforward. All right, so u is x squared y. All right, then what am I thinking here? I think I need my Jacobian. Okay, I'm not sure. I might say that in this case, because it's not super obvious, the equations aren't on the figure. V is living between 10 and 20. And U is between 20 and 40. which maybe that's something I should have been doing all along, but whatever. Okay. So J inverse is going to be ux, uy, vx, vy. So J inverse is the matrix. Okay, ux, that's going to be 2xy. Uy is going to be x squared. Vx is y, and vy is going to be x. Okay, that means that the determinant of J inverse, I'm going to do the kind of the fish-looking thing, and I'm going to get 2x squared y minus 1x squared y. That's convenient, because that's going to give me 1x squared y, which I know is equal to u, and that means that the determinant of J, regular J, is going to be 1 over u, and that's convenient. Okay, I think at this point I'm ready to set up my double integral. So we're going to be, sorry, xy is v, so I'm integrating e to the v. The Jacobian determinant is 1 over u, and then I can do whichever one I want, but I can see it's going to be the same either way. I guess I'll do du and then dv. U is running from 20 to 40, and v is running from 10 to 20. All right, now I'm going to, starting with u, that's going to be, I'll do some scratch work off to the side, because I know this is going to have an e to the v attached to it, and the 1 over u part doesn't have any v's involved, so I'm just going to factor out that value. Yeah, you've done enough double integrals. You know what I'm doing here. Antiderivative there is log of the absolute value of u as u runs from 20 to 40. Okay? I'm going to say that that's equal to the log of 40 minus the log of 20. And if you want to leave it as log of 40 minus log of 20, that's fine. That's what I did in the other one. I didn't even think to hit that one with a log property on that other problem that had this come up. But I'm gonna hit this one with a log property to say that this is log of 40 divided by 20, and that's log of 2. So I'm going to have the natural log of 2 multiplied by the integral from 10 to 20 of e to the v dv. Okay. And that would be log of 2 multiplied by, well, e to the v, as v runs from 10 to 20. Thought I was going to be able to, no, I think I should be able to fit this in. This will be log of 2 multiplied by e to the 20 minus e to the 10. That's going to be a really big number. Okay. But if you think about e to the xy over that region, you're up there where x is 1 and y is 20, and that's e to the 20 is a huge number. So it's not a surprise that this integral would come back really large. That's all the problems I've got for you for this problem set. There are more Jacobian change variables problems out there, but I think this is a good representative sample. And if you've done all these and you understand what you're doing, then you're good for my class. Thanks for watching.